Hey everybody, happy Thursday. All right, so we are near the end here of the content. We're going to wrap up with sorting and selection today. We're only going to do the basic sorts because those are the easy ones. You can look at some of the more interesting sorts in a further algorithms class. So we're going to tackle the basic ones, look at their performance of how well they perform. And then we'll do a little lab on sorting and selection on the 12th. And the 12th we'll tackle ethics, a quick little presentation and a chat around some professional ethics and organizations, which is actually really important. This is a super good topic to cover, and I'm glad it's in our program. Actually, it's part of the accreditation process too, of being in an accredited program, is that you have to include ethics throughout, so which is really good. You don't want to end up with people who don't have any ethics writing your software, or especially in data science, making bad decisions off of their data. So definitely an important topic. And then that Thursday, I'm not planning on doing anything for class, just set aside for final project work time. So we'll have time just to do some screen shares if you folks want to get chatting about the final project. And then we'll do a lab on ethics on 4/19. So I'll be on campus for 4/19, and then we'll have the final project work time. Again, no planned class, no streams or anything set aside for that, and the 21st as well. So if you folks are working in pairs, it's a good chance to get together for sure. And that's dedicated time that you all should have free then. And then we don't present until a week after that. Again, we're going to do a little bit later presentations. I've got a doctor's appointment with a specialist I couldn't reschedule unless I wanted to wait like another 3 months. So we'll probably plan to start about 4 o'clock or so. So I'll update you all with that and in Zoom, and then you folks will present your final project. And we'll have a little bit of fun and go from there. Should be a good time. So for sorting and selection, get started on those here. The two basic sorts we're going to look at are a selection sort and an insertion sort. So we'll have a selection sort and an insertion sort. Now, they both act very similar here into how these work. And honestly, I get them confused sometimes. So the idea with the selection sort is that you have a bunch of values. So we're going to make a list. I don't know, we'll just have values here. And if you just want to throw out some numbers here, we'll add them. Maybe add like 10 numbers or so here to a list, and then we'll see how we can do a selection sort to sort these things. So I don't know, like 4 and any other sort of numbers. They don't have to be in order. We can just throw them out here. 2 and a 30, 99, a 7, 12. I don't know, 15, sure. That's not quite 10, but that'll be enough. So the idea with a selection sort is we're going to iterate over the list and select the smallest item and then move it to the front. So the process, so we'll go find the smallest item, move to the front. So we'd look at every n item here and see which one is the smallest. Right, so our algorithm for this, let me bump this back down over here, maybe. So we just want a function for selection sort given some list. Right, we can sort whatever list it happens to be. So we're going to have a current position. So we'll have a current index. It's going to start off at 0. Right, that's the first location. And then we're going to loop through until we get to the end, except we don't need to do the last one here. So we're going to loop through, so we're going to say for index in range from 0 up to the length of the sum list here. And then we want to go -1, because we don't want to hit the very end. We want to start at the beginning and go up through the second to last value here. And we need to use indexes here so we can start swapping items. So what we're going to do then, we're going to look through and find the smallest item from index up to the range. So the smallest item is going to be the first one to start. So we'll have the smallest item. The smallest item is going to be my sum list at index. To start, here, I'm sorry, so we need to start that one off before here, sorry. Sum list, oh shoot. No, that's fine, that's fine. So start it off no, I'm sorry, at current index. So we'll start off at our current index here, and then we're going to be looping through all the values to find the smallest one. I'm getting ahead of myself, so we need to find the total smallest here. So we're going to start at the first one here, and we're going to range from the current index up to the length. Sorry, there's two loops that happen here. I got mixed up with which one. So starting at index 0, we're going to go from 0 to the end to find the smallest item. So I'll assume it's 0, right, as I start looping through. And then we'll go see. So we can check if the sum list at index, square braces index, is less than my smallest item, then I have a new smallest item. Right? The smallest item is going to be the sum list at index. So we can go find which is the smallest item here with this loop. But what we really need is the index value of where it is. So we actually really want to start with the smallest item index here. Make life a little easier for us. So if we know what index it's at here, so we'll go to sum list at the smallest item index. Then the smallest item index just becomes the index. So the idea is, as we're looping through, so I'm going to start here with 4. So my current index is 0. Start looking at the 4. Say, okay, the smallest item index starts here, and I'm going to look at all the next items. So then from index up to the length of the list, let's see, okay, is 2 smaller than 4? Yes, it is. So now my smallest item index will be 1. Is 30 less than 2? No. Is 99 less than 2? No. Is 7 less than 2? No. Is 12 less than 2? No. Is 15 less than 2? No. So we're going to sort through all of the remaining items to find the smallest value. Then when we're done, we're going to swap the values. We'll have a temp is going to be my sum list at the current index, and then my sum list at the current index can become the sum list at the smallest item index. Then the sum list at the smallest item index can become the temp value. So we just swap them around. So I'm going to swap my current index with 0 with smallest item index is 1. So then all of this happens here while my current index, we got to start it here, sorry, while the current index is less than the length of sum list minus 1. Back to my friend, thank you so much for donating those bits to the Student Scholarship Fund over here at the University of Michigan Dearborn College of Engineering and Computer Science. Got it in one breath. Thank you so much, my friend. You're so generous. So as long as our current index is less, here, we're going to keep on going. So after we do our swap, we're going to take our current index plus 1. This could also be another for loop too. I mean, we could do a range in here. Doesn't matter whether or not it's a while loop or a for loop. So starting at 0, then we swapped 2 and 4. So now we have 2 and 4, and now our current index will be 1. I'll say, okay, let's look at 1. Is it less than this one? Is it less than this one? Less than this one? Less than this one? It doesn't actually need to swap, but it swaps with itself. It doesn't do any harm. And then current index bumps up to 2. Right? We go back to the while loop. Current index is 2. Now we're here. The smallest item starts here at 30. Is 99 less than 30? No. Is 7 less than 30? Yep. So our smallest index will be 0, 1, 2, 3, 4, and the current index is 2. Right? So we've got, this is current here, and then we've got smallest over here. And then 7 is not less than, 12 is not less than 7, 15 is not less than, then we'll swap. We'll swap 7 and 30. And then the current index bumps up here. We say, okay, which is the smallest in the remaining amount of the list? The idea is, as we're going, we're finding the smallest value here, and we're putting it into the next position. So we just start swapping them all out. So if we were to draw a picture of this, it's a bunch of steps, but it's not too bad. We'd have, what do we have? 4 and 2 and 7, 99, 60, I don't know, and 21. I forget what the values were, but that's probably fine. Right, so we'll start here with the current index, and then we go find and swap. So then 2 and 4 swap, and then we're pointing here. We'll go find the next smallest one. That one's done. That's current. All right, this one's now current. 7 is the next smallest one. Great. We go to 99. We look at 60 and 21. We'll swap the 21 with the 99. And then we are here with current, and it is less than this. It's fine, it swaps with itself. And then the loop ends because you don't need to look at this last value because the last second to last one will swap if it needs to. So we can sort a list here. Should we do this as a, we could do this as a for loop. I'm feeling bad now here. So we'll say for current index in range length of some list minus 1. And then we don't need to increment current index. So work any better here? So as we're going, we're increasing the size of the sorted portion here, and we're decreasing the size of what we have to look through to find the next one. Now, in terms of how long is this going to take? Well, there's n items, and each time I'm doing essentially n minus 1, n minus 2, n minus 3, n minus 4, and the number of operations it has to take, right, is going to be n times n, essentially, right, because you have to do n things n times, even though it's n minus 1, n minus 2, on and on and on. Most of that stuff gets factored out. So performance of this then, on average here, is n squared. Right? The best possible case for this sort here, well, I still need to look at all n items, and every time I still need to look across the remaining n to see if it is the small. So even if you already give me a sorted list, I still have to do n squared things. I've done no work at all, but I still had to look at all of them. So even best case is still n squared. Right? And worst case, same thing. Right? I still have to do all of these things here. So worst is n squared as well. So the selection sort's not great. Definitely not great. But it could work, right? It gets the job done, and it's sort of easy to understand conceptually. So let's try it here. 4, 2, 99, I don't know, 7, and we'll see. So let's print the values list. We'll call selection sort given my values, and then we'll print values again. Now remember, if we're passing the list, we're passing the reference to the list, so changing things inside the list is fine. When we're done, it will remain changed. We didn't pass it a copy. If we wanted to pass it a copy of the list, we could slice it here. It would go sort a copy and not sort the values list. Right? So just that's one of the things we kind of talked about a little bit last semester here. So let's give it a run, make sure it works. Always test our code. 2, 4, 7, 12, 15, 30, 99. I think that looks sorted. Looks pretty good. All right, so the insertion sort is a little bit different. What the insertion sort says is I'm going to, it still will build a larger and larger and larger sorted section, but it's going to say, okay, I'm going to take for each item here, I'm going to find where it goes into the sorted portion. I'm going to insert it into the sorted portion. So if we have a bunch of values here, let's do those again. We had 7, 2, and 4, and 90, and 60 or something, I forget. It's going to say, okay, I'm going to assume this is the sorted portion. If I only have one value, it's sorted. Fantastic, great. Then for every 1 to the end here, I need to go take one at a time and move it into the correct location in the sorted position. So what it's going to do is it's going to look at the value, and if it's less than, it's going to swap its way back. So then my 2 and 7 will swap. It gets to index 0 and it's done. So now my sorted portion is now too large. Now I'm going to move to this index here. So I'm going to, if it's less than, I will swap it back. Make a swap. Okay, so 4 and 7 swap. Now 4 is not less than 2, it stops. It doesn't have to go any further because it knows as long as you're greater than the thing that comes before it, you're in the right location. So no further swapping has to happen. So then 2, 4, 7 are in order. Now we're going to look at the 90. Is 90 in the correct location? As we increase the size of our sorted position, yes, it's greater than 7. Nothing has to happen. Great. Okay, now we're going to get 60. We'll look at 60. 60 has to swap with 90 because it's less than. So we swap. And then 60 is greater than 7. No more swapping has to happen. So we're inserting the item into the sorted location just by bumping it back in place, doing swap, 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 swap here. So for the insertion sort, again, given some list, we're going to have the, for an index to sort in range of 1 up to the length of some list, right? Because if you only, the index 0 is already sorted. It's done, because there's only one item there. So we're going to loop through from the index to sort to the end. And then we're going to now loop again for our, this one might be easier as a while loop here. So we'll say our current index is the index to sort. And while the current index is greater than 0, right? And my sum list at the current index is less than the sum list at current index minus 1. So if we're greater than 0, we need to look at it. And if we are less than the thing that comes before us, if we're less than the thing that comes before us, we need to swap. So we'll say the temp is my sum list at the current index, my sum list at the current index minus 1 becomes the sum list at the current index. Nope, other way around. Change that one to current minus 1. So store the 1 here. So we would store 2, replace it with the 4, right? And then put temp back in there. Do a swap. Now, Python actually lets you do this crazy thing. I don't like it because it always confuses me, but you can say sum list to current index, comma, sum list at this equals that, comma, this. And I just hate this syntax because it's super confusing. It lets you do essentially, it does a temp all by itself. It says, okay, the first thing equals the next first thing, and the second thing equals the next second thing. And it does it at the same time. I think that's just crazy. Most of the time you'll see a temp, but Python lets you do a shorthand notation to say, okay, I want to change 2 things to these 2 things. So the book does that format here, and it drives me nuts. We want to swap. Then we're going to take our current index minus 1. We'll see if we need to swap any further. Right, so when we had, let's change this back here. So if we had 7 and 4 and 2 here, right, and then 90 and 60 or something, 90 and 60. So we're going to look at 4. The current index is 1, that's greater than 0. It is less than the thing before it, so we'll swap. So 4 swaps with 7. Current index is not less than 0, or not greater than 0, so we stop. And the reason is you need to be able to look at what comes before you. If you are 0, you can't do, well, okay, technically you can. Python lets you do negative indexes, but we don't want to be looking at the last, right? -1 is the last item. It gets really weird. So we got to make sure we're stopping at index of 1 to compare with index of 0. So that one will run. Then when we get to current index here, right, our current index to sort is going to move up then to 2. It started at 1, we sorted, that's done. Now the index to sort here is at 2. We're going to say, okay, while that current index is greater than 0, it's 2, yes it is it less than the thing that comes before it? Yes it is. So let's swap the 2 and the 7. 7 and the 2. All right, is it greater than 0? Yes. Is it less than the thing before it? Yes. Okay, swap again. So this becomes the 4, this becomes the 2. Then we're done. Now, the performance on this one is actually better. So if we were to look at, if we had a already sorted list, if we had 2, 4, 7, 60, and 90, we look at the 4, it's not less than. We look at the 7, it's not less than. We look at the 60, it's not less than. We look at the 90, it's not less than. So the best possible case is we do n operations. So this one can run quick, but why would you sort a list that's already sorted? So best case, it's already sorted, is going to be O of n. Right, because it doesn't have to do any work. It needs to look at all n items and realize there's no swapping, so it stops. The worst case is O of n squared, where if it's reverse sorted here, right, we've got 90 and then 60 and then 7 and then 4 and then 2. This one has to bump, and then this one has to bump, and then this one has to bump and bump and bump, and this one has to bump and bump and bump and bump. Here, we're doing n things n times. Right, that's the worst case. And then somewhere in the average, again, they have to move some factor less than n, but we got to throw away our coefficients. So on average, though, this one's still slow. average is still O of n squared. So it can perform better than the selection sort. But other than that, worst case and average case, it's still pretty slow. It's not a fantastic way to sort things, but it works for us, right? So some of the things we've looked at before actually can improve this performance. So we looked at using the heap for our priority queue. If you take n things and you throw them into a priority queue, we looked at the performance of a priority queue was log n to add something, right? Because it just needs to filter down where it needs to, or it puts it at the end and then upkeeps it where it needs to go. So if you're doing n things and the performance is log n, then you could sort with a priority queue or a heap sort is n log n, right? N things at performance time of log n. So you can do a heap sort without too much trouble here. It's not too bad, priority queue. It's not super fast, but it works here. We could use a binary search tree, right? The performance of that, it takes, again, log n to add something to a binary search tree here. So n log n. If you just want to throw everything in the binary search tree and then traverse it. This one gets a little bit funny with the priority queue because you have to remove items and it's going to repeat the downheaping process. So I think that one was going to be a log n to remove something because we didn't have a traversal here. So it might be log n squared? Is that a thing? Log n squared? I don't know what that looks like when you square a log. Yeah, okay, so 2. Yeah, we still throw away coefficients. So yeah, so it'll be a little slower than our binary search tree because it's destructive to remove things. Right, but we can happily throw that away because we just gotta pretend. The coefficients do matter, but in terms of, if it's 1 million things, it's still gonna be slow, even if it's 10 million. So these sorts are actually pretty decent here. Then another way of sorting things. So there's this really cool video. I can't play it though because I think it's copyright on YouTube, but it's called Sound of Sorting, which is really cool. There's let's see, Sound of Sorting. This is a really cool video. Yeah, this one here. I don't think I can actually play it on stream though, but I'll share the link.
Why I drink mushrooms every morning.
I drink mushrooms, sure. Go for it. I mean, try and get off of coffee, I guess. That maybe might be good for you, but sure. Let me share that one here. So that's a fun thing, and one of the sorts in here, it's going to go through and so it adds sound to it. It's showing you how it does a selection sort, finding the next smallest one, putting it in the order, and it shows you how many comparisons it took here. The insertion sort, right? Inserting backwards into that sorted order. The next item gets inserted back. It's really fun. We've done some graphs, yeah, that sort of look like these sort of things. It's going. Right. This one here is the quick sort. So we're not going to cover quick sort. This one is sorts of groups things into smaller and smaller and smaller groups, and then does a quick little insertion sort on them, essentially. But it does it in smaller pieces, so it performs a little bit faster. Kind of chunks it up at a time. A merge sort is a similar approach. It goes through and sorts different pieces, and then it's going to merge them together as it goes. This is a pretty common sort as well. So the problem with quick sort, it has a really bad worst case performance. Usually it's a really good sort, but if you hit the worst case, then it just is awful. So merge sort's pretty nice. The heap sort, sorting things by putting them into a heap, pulling them off the heap as you go. Remember, one of the things you can do with the heap, if you throw everything at the bottom row first, it's going to perform a little better here. So we're essentially saying, let's build out the bottom row and then the next row and the next row to minimize some of the logarithmic stuff. So you can optimize your heap sort. That's in the textbook, but we skipped it because it's interesting, but not that much. The Radix sort. This is one of my favorite sorts here. Radix never compares items to each other, which is really fun. It puts items into buckets and then grabs them out of the buckets in order. So the way that the Radix sort works, right? If you have a bunch of numbers, you're going to say, okay, if they're all 7-digit or less numbers, we're going to look at the leading digit and group them by that digit here. So I'm going to have all the ones with the leading digit of 0, leading digit of 1, leading digit of 2, leading digit of 3, 4, on and on and on. And then you'll do groupings again for second digit, and then groupings for third digit, and groupings for fourth digit. So to get the numbers in order, you take everything out of the 0 leading digit bucket, and then you look for the second digit. Well, where's the 0 in the second digit? Where's the 0 in the third digit? 0 in the fourth digit? So you can just take them out in order out of the buckets, which is really fun. And just really neat to say you can sort something without ever comparing them. But it only works on certain types. Like numeric values are really easy. You can sort strings. Other objects you just can't really sort with a Radix sort, though. We'll just go through and make all the buckets here for each significant digit. The standard sort that's built into the library in C++. I believe it's a quick sort. Let's Google that. C++. Standard sort. Is it? Which one is it here? Oh, I don't know. What link is this? It doesn't say. Come on. What method is it? That's not useful. Sort. Where is it? Sort algorithm? Doesn't even say. Okay, I'm failing. I think it's a quick sort here. Sorry. We could spend more time searching. We'll probably find it, but it's not that important. That's the built-in one in the library. Lots and lots and lots of people have looked at the standard library. We know it's a good sort. Right? Really smart people with PhDs in applied mathematics and sort of things come up with this sort of stuff. And then a stable sort. So you have two options here in your standard library, and there's some difference between the two. I think this one's a merge sort. Yeah, this one looks like it's a merge sort for the stable sort. Again, performs really well and has a better worst case time. Quick sort, it could be a little faster, but it could be terribly slow. Essentially, if you give it a backwards sorted, the quick sort sucks. So stable sort with the merge sort, you'll perform better in some cases. The shell sort, I've Googled this one before. It's a hybrid approach, I think, between merge and quick sort. I don't remember offhand. We could Google it and see. It's much more fun with the sound. I'm sorry. You'll have to listen to it later. The bubble sort is more of a toy sort. Essentially doing a backwards insertion sort. It's got some other fun things to it. That one's just for fun. The cocktail shaker sort, we're twice as fast now as a selection sort because we're sorting the smallest and the largest at the same time. We go back and forth, back and forth, back and forth. So we're kind of optimizing the number of times we have to go through that array. It's just a silly one. The genome sort, I don't know how this one works. I have to Google that one again. Been a little while. I think they've got, yeah, I think their website has more information about it here. They've got all their sorts. Bit-tonic sort, yeah, I gotta Google this one too. This one's crazy. All right, that was pretty fun. I think they've got one last one that's just really silly. And we'll look at it for a second. all right, the BOGO sort is just randomly picking one until they find a value. This one's just totally silly. All right, but the sorting is really neat. So a couple different ways of doing some sorts here, all about performance, right? Ideally, we want to use the fastest one here. So we're probably never going to write our own sorts because let's be honest, we're not going to come up with anything faster than people have already come up with. But we want to understand how they work so we can see why they perform in the way that they do. That's kind of the goal with that one. All right, so we commit this one. Oh, we should make sure insertion sort works, right? That's we didn't test that one yet. All right, it seems to have worked here. 2, 4, 7, 12, 15, 30, 99. All right, so we get them in sorted order. Again, this will be a little bit faster than the selection sort, and that's about it. All right, we commit those. So, and I did want to talk a little more about the final project. We ran out of a little bit of time there at the end here. So as we're doing our Yahtzee odds, one of the things we want to do here, instead of actually brute forcing every single possible mathematic approach, as we're doing our modeling here, this largest possible score, what we can do is this thing called a Monte Carlo approach, where analysis? Yeah, I think it's analysis, or simulation maybe. Monte Carlo method. So instead of actually saying, hey, there are 6 dice, right? And we say 5 dice, each with 6 sides, right? So all the different possible ways, I think I was doing this backwards before. 5 dice, each with 6 sides, should be 15,000 possibilities, outcomes here. And again, this is combinations, this is permutations, not combinations, which don't actually matter. We only really need the combinations here of all of these. So we can do some other math to find out, but we don't want to do all this work. So what we can do with the Monte Carlo method is we just do a random sampling and say if we can get some random results here and say let's just do 10% of what we would have had here. I could say, okay, let's just do 1,500 random rolls. I'll say, okay, just randomly generate what could happen, not here's all the 15,000 actual possibilities here. We're going to do a small sample of that and look at the subset and say, okay, well, what happens if we roll these 3 dice? What happens if we roll these 2 dice? What happens if we roll this 1 die? Because this is 15,000 ways could happen if we roll all the dice. But if we only roll 4 of the dice, then there's 4,000 different rolls we could have where we kept 1 die. Right? And then there's 5 different dice we could keep. So each of these then would be across each of the 5 different dice. So if I kept die number 1 and rolled dice 2, 3, 4, 5, I'd get 4,000 different ways. If I kept die number 2, rolled these ones, right, get another 4,000, and it just piles up larger and larger and larger, right? 3 dice with 6 combinations here is 729 different possibilities. But how many different ways can I get? So we need, Wolfram Alpha is much better at this than the Google searching, right? So if we are keeping 2 out of 5 dice here, so 5 in combination 2, 10 different ways here. And then if we're choosing 3 dice to keep out of those 5, right? Is that still 10? Yeah, okay, that's fun. Choosing 4 dice to keep, right? How many different ways can we choose 4 dice to keep? 5 ways. So we're like multiplying all the different odds across, and that's going to be a lot of work to do. So we don't want to have to necessarily simulate every single possible way. So we want to do a random sampling and say, hey, let's just do 10% here, to say, okay, this is likely odds here, not the actual odds. So this will speed up our analysis here, and we should get essentially close enough because we do get a nice uniform distribution when you come to rolling dice. This only really works here when you've got good distributions here. If you don't have good distributions, you can't really say, oh, let me just pick a random value here. It takes more work to generate random values on a non-uniform distribution. Like if we want to look at weather, for example, you don't just have a random temperature between 0 and 30 degrees Celsius, or like -10 and 30 Celsius, right? We've got a pretty good distribution of here's the lowest it's ever been, here's the highest it's ever been. Most of the temperatures will fall within that center range, but you do have the outliers. So there are ways to do this that take a lot more math. We're not going to worry about it, and dice just have a perfectly even distribution because it should be perfectly random. You get a 1, a 2, 3, 4, 5, or 6. They're all a 1 in 6 chance. here. So this will work really well for us to not have to do all of the work of mathematically choosing every single possible outcome. We'll just say, oh, let's just ask for random dice rolls and see what happens. So the goal here is if you have 5 numbers, what will give you the most possible points that you could score? So you could roll all 5 again, and if I do that 1,000 times, what score did I get from each of those kind of across that 1,000? So we're going to sum them all together and say, okay, the sum score that I got from rolling all 5 across all the different chances was so-and-so. Then how about if I kept this one and rolled these 4? What's the total score that I get across all the different chances? So I multiply them out to see what's the possible score to see there. And that's how we're going to predict the future, which dice do we roll to get the best possible largest score after that next one roll. So it's not the entire Yahtzee game. We don't need to simulate. We have 2 different rolls and you can keep different combinations. That's again going to get even crazier. Using our approach, we might be able to. We'd have to do a little bit more limiting. But again, that's beyond what we want to tackle right now. We're just going to say, I've rolled the dice 1 time. I get 1 more roll. It's not the real Yahtzee game, but it's enough for us to say what is probably best going to happen. Right? We'd get better results if you could keep next sort of dice and we could give it some strategies and try and bundle them together. But you should see you'll get a larger score if you keep the 6, roll another 6, and keep that 6. Like the math should prove out, yeah, that was the better choice for us. But again, that's a little bit more complex than we want to tackle in this is likely your second programming class ever. So just this first level simulator here. What happens if I roll all 5? What happens if I roll 4 of them? What happens if I roll 3 of them, roll 2 of them, roll 1 of them? If I just keep my score, right? There's no other random chance here, so that's just what score is it? And that might be your best score, right? If you already have 24 points, just keeping that is probably going to be a better score than rolling again, right? Rolling any number. There's the 1 in 6 chance you could roll the 5th 6 there. So 1 in 6, then you'll have a 30-point score, and 5 out of 6 are you keep your 24. So maybe that actually works out better when you look at that math. So should be interesting to work out here as we start building out our little Yahtzee simulator. So from where we have the dice to simulating and saying, hey, we suggest you roll die 1, die 2, die 3, die 4, die 5. Ask the user, okay, which dice do you want to re-roll, that sort of thing, and plug it in. So we're not playing against a computer. This is just single player mode here with the prediction. The other piece of this that makes this trickier, though, is as you're playing the game, you have less places you can score the points. So once I've scored a bunch of these values here, come on, Bill, just go. I want 1 player. We'll roll. Right? After I've scored some of these, I no longer have the chance to score them again. So if I've already scored my 6's score here, and I get 4 6's, I can't score it in 6's. I might be able to score it in a 4 of a kind, or I might possibly get the Yahtzee score, but that's going to change the predicted future value, because if we have scored all these other ones here, sure, we'll keep that one. You can't score it again a second time that game. So the exact same roll will give you a different future value based on what you've already scored. Right? At the beginning of the game, when you can score it anywhere, you have the most opportunities to score, but near the end of the game, you literally just have to take your last roll, and it might be a 0. Right? If you can't score it anywhere, you just get 0 points. Right? I rolled no 2s. Hey, I get 0 points there. I rolled no 4s. Right? It's a possibility. So as the game progresses, it's harder and harder and harder to score the points. So we have to keep your scorecard as part of that as well, to say what's the best possible future score based on your current scorecard. So kind of designing this, right, we need some sort of way, and probably a class, right, as we think about a scorecard's kind of like a noun, right? It's a thing and it has attributes, like what you've scored, what you haven't scored, that sort of thing. So that could be a noun with different attributes, right? The set of dice, maybe you want to store that as a single thing. Maybe you just have 6 different dice or 5 different dice, or maybe you just use random numbers. There's lots of different ways of dealing with that there, but you need to know what the current values are, so then you can look at the future values and see your possible scoring here. So you need a way to take a given 5 dice to see what scores you could get out. So 5 dice given a scorecard, you have places you can score it based on what you've already scored or not. So there's a lot of pieces that go into this here as we go. which I think makes for a fun project. So, and lots of different ways you can go about it. You don't necessarily have to use any classes there, but I think it'll make the work a whole lot harder for you. Right? If you can say, hey, given a scorecard that already has something filled out or not here, and my dice, what can I score possibly, is going to make it easier for you to predict this future possible score, rather than trying to figure it out every time. So a couple of fun things we can go through from there. And did I commit this? I think I was working on that, and I got distracted. All right, so that's all we got for today. Next week, Tuesday, lab on sorting and selection. So we'll look at sorting, see if we can time some of these things. We'll try our heap sort and our binary search tree sort. We've got a couple different ways of doing some sorts we'll play with. Here, the insertion sort and selection sort are given to you in the textbook, so the copy paste is kind of boring, but we'll try and see if we can't time them out, or do some of that timing analysis like we did with adding values to our lists. And then we'll talk about ethics Tuesday. No planned class on Thursday that's set aside for final project work time. We'll do an ethics lab the following Tuesday. And again, no planned class, just project work time for that last week. And so we'll have 2 more labs and 1 more class, essentially. So 1 more class on the 12th, lab on the 12th, lab on the 19th, class on the 12th. No class meeting 14th, 19th, or 21st. It's just set aside for you to work on your final project. Again, people used to come in person and they could sit next to each other and talk, but we have all sorts of online collaboration tools now. But the class time should be free for everybody. So for sure, that's great to work with partners, and I wouldn't feel so bad trying to make busy people work together because, hey, you've got 6 hours between all these different classes or whatever to work on it here. The ethics lab also won't take you the whole hour 45, assuming the door can be unlocked. So you should have some time after the ethics lab as well if you wanted to work on that. It's a quick little experiment and then a write-up. What would you do? It's not a whole paper, don't worry. It's like a paragraph. It's not nothing too bad here for writing. And then final project presentations, and we are done with the winter semester, believe it or not. So it's been a lot of fun. I got the first project graded. I'm still working on 1 and 2 here. Hopefully you know how you did based on the rubric, right, as you did your little self-assessment. So I apologize, they're late. I'm working on getting those in. All the labs should be up to date, and we'll go from there. Okay? All right, folks, you take care. I will see you on Tuesday then.